I'm Brian Wright from Facing Future, and we're talking with Paul Beckwith.
Hi, Brian. I thank you for interviewing me today and having me on.
Well, I have a great interest at the moment in the oceans and the health of the oceans, or the disaster that's happening in the oceans, rather, which has many aspects to it. And I hope you can take us along a path towards understanding the complexity that is the state of the oceans.
Yes, there was a paper recently that was talking about tipping points in the oceans, and basically it was talking about three main points. Of course, the first one is the extent of the ocean warming. And it's not just the warming at the surface. The sea surface temperature has been, rising quite rapidly. And of course, when the sea surface temperature is over 26.5 degrees Celsius down in the tropical regions, then any small disturbance that then propagates and enlarges and strengthens into a tropical storm becomes amplified that much more by water temperatures above 26.5, because there's a lot of evaporation, of course, from such warm water temperatures at the surface, and then a lot of water vapor is put into the air, which then rises up and condenses into droplets and clouds and releases tremendous amounts of energy, which builds up the intensity of these hurricanes or cyclones or typhoons, or call them what you want. So, we had a large one very early in the year that just that hit the Philippines, and these storms are going from a tropical disturbance to full Category 5, in record short times, and they're very very large storms, and often they don't move as quickly across the surface. So when they do hit an island or a continent, they tend to linger and be there for a long period of time. For example, Harvey, when Hurricane Harvey came ashore and hit Texas, it was only moving at a few miles an hour, a few kilometers an hour. So it affected Texas. It was like connecting a fire hose from the ocean to the land. So warming of the oceans is a huge deal. And, the warmth, of course, propagates down through the depths into the ocean. So the upper layers are warming much faster than the lower layers. And of course, warm water is lighter. So when the sea surface temperatures are very warm, there's almost like a layer or a lamination of the ocean, the heat, and you get less vertical mixing, which is vertical mixing is needed to bring oxygen to lower depths and to bring carbon to lower depths and things. And when you have less vertical mixing, you get stratification of the ocean, and that's the problem. The thermohaline circulation, so thermoheat, saline, the saltiness, and like, for example, the Gulf Stream coming up the eastern coast of the U.S., as it moves north east, it carries tremendous amounts of heat over to Europe, and the Gulf Stream has been slowing down, and it's overrunning the continental shelves of the U.S. more. So we're getting record warm temperatures down to depth over the continental shelf off the eastern U.S. Most noticeably, scuba divers in Maine, for example, they go down 50 meters, and the water temperatures are unbelievably warm. Of course, the warm surface waters are having huge negative impacts on the coral reefs. And in the Pacific side, it's the Kuroshio current, which is sort of their equivalent to the Gulf Stream, and that's also been exhibiting slowing. So yeah, the whole heat transfer on the planet is being disrupted generally, of course, the equators are warm, the poles are much colder, so heat has to move from the equator to the poles, and it does so via the in the atmospheric wind currents, which sets up the jet streams, and also in the oceans. About 2/3 of the transport of heat is in the atmosphere, and about 1/3 in the ocean. So the ocean warming also means that the warmer water is less able to dissolve gases as much. So that means the oxygen. So deoxygenation of the oceans is becoming a huge problem. Not just dead zones from phytoplankton blooms in coastal regions, but we're getting dead zones in the ocean where there's just not enough oxygen for marine life to thrive, to survive even. And of course, the ocean acidification is the huge major factor. The oceans are acidifying rapidly, and the pH of the open ocean has decreased. So the oceans are becoming more acidic, about a 30-40% increase of acidity over what we had pre-industrial. And that the ocean acidity has remained stable for many tens of million years, 30 to 40 million years, and now it's dropping very sharply, the pH, meaning that and it's starting to affect excuse me, shellfish, and forming their exoskeletons, and also phytoplankton, forming their little microshells, calcium-based microshells. So the ocean is under huge stress. That's not to mention, the overfishing and the other sources of pollution in the ocean.
So what is causing the acidification? Is it the CO2 in the atmosphere?
Yeah, it's the CO2. The CO2 levels are higher, much higher in the atmosphere, and we've just passed 420 parts per million. So we started about 280 at the end of the last ice age. So we've gone up 50%, and the CO2 forms carbonic acid in the water droplets in the air, and then when that falls, that carbonic acid is what is causing the increase in acidification of the ocean. So so that this is, and it's already having a big effect on marine life. It's another stressor for coral reefs, not just the warm temperatures, but also the so the acidification. It changes the what's called the calcium compensation depth, and when there's calcium, so it's the calcium carbonates, it's the calcite and the aragonite are two different types of the calcites that are used by marine life to form their shells and so on. So when the pH, so we're kind of near a tipping point or threshold of acidification if it drops much more. So it was about the ocean is still basic, it's versus acidic, but it's tending towards the more acidic side. And when the pH drops below about 7.8 or 7.9, then it's really difficult for phytoplankton, for example, to form their shells, their calcite shells and aragonite shells. And so that it basically will transform the phytoplankton, how they behave and how they exist. And of course, they're the base of the food chain in the ocean. So it's a very serious issue, the ocean acidification.
Why is it acting on the polar regions more than the other regions of the Earth?
One of the main reasons is that there's a whole bunch of reinforcing feedbacks which are accelerating the process. And the biggest one people talk about is the reflectivity of the material on the surface in the Arctic. So when there's lots of snow and ice, that reflects a lot of the sunlight and that keeps it cold. But because we're losing snow cover on land in the spring mostly, and we're getting less and less Arctic sea ice. We're getting more and more melting in the summers. The Arctic is becoming a darker place. It's not reflecting as much sunlight, and therefore it's absorbing more sunlight, and it's warming much, much faster. So if you look, if you're looking down on the Arctic from a satellite, the total reflectivity of sunlight used to be about 52% from the entire Arctic on average, and now it's about 48%. So that difference is actually, may seem small, but it's quite significant. And so we're getting that much more energy being absorbed by the surfaces in the Arctic. So we're getting tremendously large warming. So, for many years, most publications and mainstream press, et cetera, would say the Arctic is warming at twice the rate that the rest of the planet is warming at. But that number is actually, and now they're saying more like 3 times, but that number is actually more like 4 to 8 times, depending on what latitude you're at. So the higher latitudes, the closer you are to the pole, the faster the warming. This is also happening in the southern hemisphere. As you go closer to the pole, the rate of warming is increasing. So when the Arctic is much, much warmer, that temperature difference to the equator is much, much smaller, that temperature gradient. So the jet streams, they slow down and they become wavier in the north-south direction. So there's very, very, high ridges in the waves, and heat from lower latitudes and moisture goes up into those ridges. And sometimes those ridges extend right to the North Pole, and we can get temperatures above 0 and a lot of moisture in the dead of winter. When it's completely dark at the North Pole, we can get above 0 temperatures. And by the same token, the troughs of these jet stream waves go very, very far south and can bring very, very cold weather to far southern regions. So Europe just experienced a strong ridge with very, very warm, record-breaking warm temperatures for March, towards the end of March. And then the jet streams shifted over and they became in the trough, and they experienced record cold temperatures for that time of year. And of course, these shifts are causing a lot of what I call weather weirding or weather wilding or weather whiplashing, where you go from one state to the other state. So there's a lot more heat in the Arctic, and that's why the air temperatures are setting records up in the Arctic, and the water temperatures are setting records up in the Arctic. So the water temperatures are a big concern, especially when you're over the continental shelves. And these continental shelves in the Arctic are enormous. So think of the Eastern Siberian Arctic Shelf. It's one of the largest in the world, actually. And Peter Wadhams has described some of his trips up there where they measure the water temperatures down to the bottom of the, on top of these continental shelves. So it's not that deep. The water might be 50 to 100 meters deep. And he's seen warming of 4 or 5 degrees Celsius in that water. And of course, that warm water is a concern because then it thaws the sediments underneath, and there's methane clathrates in the sediments. So it's a huge problem in terms of causing methane release. Is one of the, so there's all of these cascading sort of knock-on effects that are greatly warming the Arctic. And that causes us further south to see much wavier jet streams. And so we're seeing great increases in the frequency, severity, and duration of extreme weather events, whether they be torrential rains leading to flooding or heat waves leading to drought. And we're also getting lots of these marine heat waves as well. In some upwelling areas, we're getting huge sort of acidification events where the acidified water from deeper down comes up towards the surface and causes huge effects. So it's like an extreme acidification type event. And then after the water mixes, then it can drop off a bit. But So we're getting these events that we're seeing on land, and we describe and experience them. So, they are the forefront of our minds. These things are also being seen in the ocean as well.
So the oceans really are at a big stress point of being affected by these temperature changes and also acidification. So what does that do to the plankton and the food chain that comes out of the smallest microorganisms?
Right, because they're plants, so they need the sunlight, right? And as you go deeper in the ocean, there's less and less sunlight. It's absorbed in the water column. So they exist at the surface, and the surface is where the greatest warming is occurring. And when we think of global warming, climate change, we think of how we're affected and the atmosphere is affected and temperatures are rising in the air. But 93% of the heating of the planet is actually heating of the ocean. So 93% of the energy that's absorbed on the planet it goes to heating the oceans, and it's only that 7% that heats the air that we mostly talk about. So the oceans are, there's tremendous changes to the oceans, and some of the recent phytoplankton studies showed a big decline in phytoplankton. There's a couple of different things. There's they also need, like any other plant, they need nutrients. So they get, there's lots of CO2 in the air. There's lots of CO2 going into the oceans, right? So the plants have the CO2, and they need, they use fresh water in the photosynthesis process, and they get the water from the ocean, and they have the sunlight, but they also need nutrients. And there's vast regions of the oceans where, if you think of the Caribbean islands, for example, the water is this characteristic blue color. It's almost like, the cleaner that you put in your toilet bowl. It's that bright blue color. And the reason it's that blue color is that's the sort of natural color of the water. What makes it much darker in most of the ocean is phytoplankton and sediments and things. But the water in the Caribbean is so warm, there's very few phytoplankton, so it has that blue type appearance. So there's lots of regions of the ocean that are mostly devoid of phytoplankton. So they're almost like deserts, if you like, for life, in terms of very, very low amounts of life. Because if there's low phytoplankton, that's the base of the food chain, there won't be a lot of other life. So there's some of these regions have sufficient nutrients for phytoplankton to proliferate, but they're missing iron. So iron naturally gets into the ocean from when there's dust storms in the Sahara, for example. Those are carried out across the ocean, and the dust contains iron, which fertilizes the oceans and causes phytoplankton blooms. So one of the most promising ways to do carbon dioxide removal is to stimulate the growth of phytoplankton with iron. So there's a couple of different methods. There was, if you put iron into the ocean in the form of iron sulfates or things, I think it was, then we've seen phytoplankton blooms in those trials, which have been very few, but there have been some. But there's something called iron salt aerosols, where if you generate these iron salt aerosols, the iron acts to stimulate phytoplankton, and the iron salt aerosols act to create low-level clouds, which will then block some of the sunlight and cause cooling over a region where they're distributed. And they also contribute to helping break down methane, which is another benefit. So people are looking at some of these these groups. I mean, for a long time, I've been talking about, sort of a three-legged bar stool of what we need to do to try to stabilize the climate. And of course, we need to slash fossil fuel emissions as soon as possible, as quickly as possible. That's one leg of the bar stool. And then another leg is carbon dioxide removal and methane removal from the atmosphere. And then the third plank is solar radiation management methods to cool us a bit and to buy us time before we rocket up to say an ice-free Arctic. So I've talked about those sort of things, and they're of course very very controversial things, but our climate system is changing so quickly and so abruptly that we're crossing these thresholds or tipping points on multiple different elements of the climate system. So definitely the Arctic sea ice is right up there. It's number one, along with the Amazon rainforest. It's sort of flickering or wavering, and some drought years there, it's no longer carbon sink. And the danger is in fact, for all terrestrial vegetation, with business as usual, in about 20 years, according to a recent paper, then the entire terrestrial biosphere of plants will no longer be a net carbon sink, and it will become it will lose the capacity to be a carbon sink. So we're in grave trouble, of course, when our sinks are failing, because then the greenhouse gas levels, specifically carbon dioxide, will skyrocket in the atmosphere. We're already seeing worrying signs, both in CO2. We passed 420 parts per million recently, and we're also seeing, in methane too. I mean, some people have sent me some data on methane, and the methane curve where it goes up and comes down and goes up. That cycle seems to, it should be halfway through the cycle and going down, and it started to rise up again. And this is at some monitoring stations in the Arctic, and it's very concerning. What's happening. I mean, we're seeing lots of surprises in the climate system. As we become more and more destabilized.
I've seen reports and pictures of phytoplankton blooms, which are the result of fertilizer spillage into rivers and into the oceans. That's always talked about as a bad thing.
So, the Gulf of Mexico is a perfect example. So after the farmers fertilize their fields, and there's runoff, big rainfall and runoff of these phosphates and other fertilizers into the Mississippi River, and then they're carried into the Gulf of Mexico, and it creates a phytoplankton bloom. And then the phytoplankton, it's not a sustainable bloom, so the plant matter dies and sinks towards the bottom, and then all the microorganisms digest it and eat it up, and that depletes the oxygen at the bottom. So you get a massive dead zone in the Gulf of Mexico, and it can travel up through the water column, but it's mostly lack of oxygen down below, and that it's exacerbated by the very warm temperatures, causing the stratification and reducing vertical mixing in those regions. So that's one thing. What the key difference is, you want to create if you're creating phytoplankton blooms by fertilizing the ocean, you want to do it in the deep ocean. Okay, that's the key difference, because if you have the phytoplankton bloom in the deep ocean, when that plant matter is digested by zooplankton and then goes up the food chain. So zooplankton are the very tiny animals which eat the plant matter, right? They're the next trophic level in the food chain in the ocean. Then they'll eat it, and then they'll excrete material, which then sinks to the ocean floor, and the plant matter that dies will also sink down, and that carbon eventually gets into the sediments and so on. And so it's taken out of the system for a long period of time. So you don't want the phytoplankton, you want the phytoplankton blooms basically in deep ocean water. If you're disrupting the phytoplankton at the base of the food chain, and that's, you're either by, well, you're definitely changing, the acidification of the ocean is definitely changing the character, the life cycle of the phytoplankton. Because if the ocean's too acidic, then they can't form their shells, and their shells are kind of for sort of protection, and it gives them some weight, right? So one of the ideas is, when they die, then the shells have some weight, and it can cause them to sink slowly over time. Without shells, there'll be less of them mixing and going downwards, and with stratification, less of them going downwards. So the carbon sink of the ocean is threatened by the great warming of the water, and by the acidification. And we've already mentioned the deoxygenation effects. So that when there's not enough oxygen in the water, then the zooplankton and other animals all the way up the food chain get negatively affected, right? There's just less of them, and their actual, life cycles and the timing, the phenology, I guess, everything changes, and you get much less marine life overall. I mean, and then add to that the stresses from overfishing and bottom trawling and all these other things. And what people are doing is we're getting more and more of our food from the ocean comes from these aquaculture type farms that are mostly on coastlines. And if they're monoculture, they're also a big problem, because you need to apply permaculture methods to marine to marine aquaculture, and have, you don't want monocultures of anything. You want a thriving ecosystem, because then there's a lot of synergistic effects that are very beneficial to having much higher growth of things, but to feeding livestock, which we then eat. So but if you think of the marine equivalent of this, I read an interesting book a few years ago called Seasteading, and it was looking at it suggested that the whale shark could be domesticated, like cattle, for example. If we domesticated the whale shark, the reason why the whale shark would be a perfect candidate is it tastes reasonably. It tastes pretty good. The fish, they're enormous. They're actually fish and not sharks, really, right? They're enormous creatures, and they have they're gill feeders, so they actually bypass many trophic levels in the food chain, where you have phytoplankton, zooplankton, small fish eating the zooplankton, and bigger fish, all the way up till you get the top of the apex of the food chain. The sharks are they're huge fish. So the whales are eating the krill, and so it bypasses it. So it's very efficient way that perhaps getting lots of fish for huge volumes of meat from the whale sharks. If you imagined electronic pens or some sort of big pens in the middle of the ocean as part of a permaculture system, where if you generate a phytoplankton bloom with fertilization, and you have anchor points that go down to different depths, then you can start getting you're in the middle of the ocean, right? The water's like thousands of meters deep, but if you have anchor points and platforms and things, you could have your phytoplankton bloom and zooplankton, and then you could have shellfish, and you could have oysters and clams, and you can have an entire ocean ecosystem sort of, near the surface of the ocean. And then you could have, massive sort of pens of whale sharks, and you could feed huge numbers of people and try to stabilize the climate system of the Earth. So those would be, sort of massive tipping points in who we are and what we do and what our priorities become.